We start with a point.
Hi, it's Rob Bryanton and welcome back. Imagining the 10th Dimension video blog. Today's entry is called The Invariant Set. And the video you're looking at over my shoulder is also here on YouTube. I've become a big fan of Charles Gilchrist, and he's into sacred geometry. And we're going to be talking about some physics ideas here, but at the end of the video we'll talk a little bit about how Charles' video, which is called 7 Pennies, ties into that. Now, Gavin Gerbrand called it SOAPs, S-O-A-P-S, the set of all possible states. For our universe, I called it a point in the 7th dimension. And for the omniverse of all possible universes and information patterns, I called it the 10th dimension in its unobserved state of perfectly unfolded symmetry. Now I'd like to read some excerpts from an article in the March 30th, 2009 issue of New Scientist magazine that explores a concept from physicist Tim Palmer called the invariant set. I would say we're all talking about the same thing, viewing the universe from a timeless perspective. And the article I'm going to read from here is called Can Fractals Make Sense of the Quantum World? An article written by Mark Buchanan. Quantum theory just seems too weird to believe. Particles can be in more than one place at a time. They don't exist until you measure them. Spookier still, they can even stay in touch when they are separated by great distances. What if there were a way of showing how quantum theory might emerge from a deeper level of non-weird physics? If you listen to physicist Tim Palmer, it begins to sound plausible. What has been missing, he argues, are some key ideas from an area of science that most quantum physicists have ignored: the science of fractals, those intricate patterns found in everything from fractured surfaces to oceanic flows. Palmer's ideas begin with gravity. The force that makes apples fall and holds planets in their orbit is also the only fundamental physical process capable of destroying information. It works like this: the hot gas and plasma making up a star contain an enormous amount of information locked in the atomic states of a huge number of particles. If the star collapses under its own gravity to form a black hole, most of the atoms are sucked in, resulting in almost all of that detailed information vanishing. Instead, the black hole can be described completely using just 3 quantities: its mass, angular momentum, and electric charge. Many physicists accept this view, but Palmer thinks they haven't pursued its implications far enough. As a system loses information, the number of states you need to describe it diminishes. Wait long enough and you will find that the system reaches a point where no more states can be lost. In mathematical terms, this special subset of states is known as an invariant set. Once a state lies in this subset, it stays in it forever. A simple way of thinking about it is to imagine a swinging pendulum that slows down due to friction, before eventually coming to a complete standstill. Here, the invariant set is the one that describes the pendulum at rest. Because black holes destroy information, Palmer suggests that the universe has an invariant set too, though it is far more complicated than the pendulum. Complex systems are affected by chaos, which means that their behavior can be influenced greatly by tiny changes. According to mathematics, the invariant set of a chaotic system is a fractal. Fractal invariant sets have unusual geometric properties. If you plotted one on a map, it would trace out the same intricate structure as a coastline. Zoom in on it and you would find more and more detail, with the patterns looking similar to the original unzoomed image. Gravity and mathematics alone, Palmer suggests, imply that the invariant set of the universe should have a similar, intricate structure, and that the universe is trapped forever in this subset of all possible states. This might help to explain why the universe at the quantum level seems so bizarre. The key is the invariant set. According to Palmer's hypothesis, the invariant set contains all the physically realistic states of the universe. So any state that isn't part of the invariant set cannot physically exist. In a paper submitted to the journal Proceedings of the Royal Society, He shows how the basic idea can account for quantum uncertainty, contextuality, and other quantum puzzles. Now, I've talked before about fractals and recursion and how these relate to this way of visualizing reality. While Dr. Palmer is not talking about extra dimensions with his theory, it's very easy to use his invariant set concept in the context of my project. In entries like "The fifth dimension isn't magic," "Our non-local universe," and "Aren't there really 11 dimensions?" I've talked about what's possible and impossible within this way of viewing reality, and how the logical progression from one spatial dimension to the next that I'm portraying gives us a way to see how the universe, the multiverse, and the omniverse are related to each other. Each is a subset of the next, and all make more sense when we learn to view from the perspective where, as Einstein liked to say, the distinction between past, present, and future is meaningless. I mentioned that with my system, I would say that our universe's invariant set is locked in at the 7th dimension. This can also be connected to the string theory idea that our 3D universe is constrained by a 7th dimensional brain. Now let's talk about this lovely video by artist Charles Gilchrist that we've been looking at here that shows a connection between the number 7, fractals, infinite recursion, timelessness, and the forms of sacred geometry. And I do want you to go to check that video out. We'll give you a button here, and we'll let Charles speak for himself on those ideas. Next time around, we're going to talk about illusions and reality. My name's Rob Bryanton. Enjoy the journey.